Okay, welcome everybody to our tTmu seminar on time, temperature, and chemical potential dependence in quantum field theories. Today we are very happy to have Markus Heyl from the Max Planck Institute for Physics of Complex Systems in Dresden, and he will talk about quantum many-body dynamics in 2 dimensions with neural networks. So please take it away.
Yeah, thanks a lot for the introduction. And as I said already before, let me emphasize again in the beginning that I'm very happy to speak at this more high energy physics oriented seminar. My background is more on the quantum many-body physics side, but to my impression in recent years, there's more and more overlap between these fields, in particular when it comes to dynamical phenomena such as particle collisions or string breaking, or more generally dynamics and lattice gauge theories. So in my talk I will unfortunately not have time to talk much about these overlaps, but more on technical aspects, which is how to access in a numerically exact way the dynamics in 2+1 dimension, which goes beyond what you can do with other methods such as tensor networks. But before I start, I would like to acknowledge one particular person, Markus Schmidt, who has been a postdoc in Dresden, and in the meantime he moved to UC Berkeley as a Leopoldina postdoc fellow. Without him and his continuous efforts in this project, which was really a long time of suffering, without his efforts, this would not have been possible. Now, let me start with the following, that in the end, we are all familiar with the fact that most or many physical settings can in the end be described by equilibrium statistical physics. However, there are also many other settings in nature which are of inherent non-equilibrium character, and some of them you might know much better than myself. So one instance, for instance, particle collisions, or the process of string breaking, where you pull apart maybe say 2 quarks, and because of the linearly increasing interaction potential between 2 quarks, at some point it becomes more favorable to break your string and to generate new particles, which leads to the formation of new mesons, say. Although I'm very much actually interested also in these dynamical phenomena, what I would like to focus on in the following is physics from a different fields from quantum many-body physics, and much of the efforts in this field are mainly driven, or to a large extent driven, by the tremendous progress on the experimental side in systems which now go under the name or under the umbrella of quantum simulators, where you can see here, for instance, the image of some gas of bosons, where each of the individual dots that you see is the location of a single quantum particle. So this is just to illustrate what these quantum simulators, for instance, can do. They can give you, for instance, snapshots, projective measurements of each individual particle that you have in your quantum many-body system locally. And that's, of course, fantastic. That's something you cannot have in any other experimental context. Now, being able to probe your system on a completely different level is just one aspect of these quantum simulators. The other aspect is that what they have achieved is, with an unprecedented control, to realize coherent dynamics of quantum matter. That means, in the end, what they have realized is the most pristine version of the fundamental equation of quantum mechanics, which is Schrödinger's equation for many-body systems. So in other words, what these quantum simulators would like to do for you, they want to realize dynamics that is governed by Schrödinger's equation without, or negligible coupling at least, coupling to any other degrees of freedom in the environment. And to some extent, that's like the main aspect of my work, which is studying Schrödinger's equation for many-body systems. And as I was emphasizing, not only from a quantum many-body perspective, but actually this interfaces also with many other fields like condensed matter, quantum many-body physics, but also high-energy physics, and the fields of quantum simulation and also quantum information. Now, let me quickly outline my talk. So first, I would like to give you a very brief introduction into some aspects of non-equilibrium dynamics, and in particular, to focus on the methodological aspect of it, and the challenges that we are facing there in describing quantum many-body systems. Then I would like to present to you one relatively simple solution to study dynamics, which we've called classical networks. And then I will use these classical networks afterwards to describe the very interesting phenomenon that can appear in lattice gauge theories, which is called disorder-free localization. And I will explain to you, of course, what that means. And in particular here, I will study the dynamics of a 2D lattice gauge, 2+1D lattice gauge theory, which some of you might know also from a high energy physics perspective, namely the U1 quantum link model. And finally, in the end, after all this preparatory work, I would like to discuss a more general approach to non-equilibrium dynamics in higher dimensions, which is based on neural network states. And please, I forgot to say one thing. Since my background is more from the quantum many-body physics point of view, it might be that I use some jargon that you're maybe not familiar with, so please feel free to interrupt me at any point. Okay, let me say a few words about non-equilibrium dynamics of isolated quantum matter. The main thing I would like to advertise here is that we are today, and that's really like just now, at a key turning point, both in theory and experiment. In that, on the side of the experiment, there is an increasing effort in realizing the coherent dynamics of quantum matter in 2 spatial dimensions. And there are various experiments which are pushing the frontier in this direction. On the theory side, however, we are facing a severe limitation when it comes to methods which are numerically exact. So when we consider the dynamics of interacting systems. And as you might be familiar with, like, we have very efficient methods to describe the non-equilibrium dynamics in 1 spatial dimension. DMRG, MPS-based methods, tensor networks, which work in 1+1D. There's also like a very successful theory for the high dimensional limit, which becomes asymptotically exact in the limit of d dimension to infinity. And this is called dynamical mean field theory. But in between, in particular in the physically relevant dimensions 2+1D and 3+1D, there's a huge gap, and there is no currently no available method which allows you to numerically exactly compute dynamics beyond some short time or small system size limitation. Now, why is it difficult? And like what I'm saying here is more like you'll know about this. So the the problem why it is hard to do dynamics is that for dynamics, we have to consider quantum many-body states, which have the following property, typically. So if you take a generic quantum many-body state, such as like some that you obtain out of some non-equilibrium dynamics, when you expand or express this quantum many-body state in some computational basis, here for simplicity in the basis of some spin configurations. So I will just consider spin 1/2 systems in the following, but everything I say will also be valid for systems made out of other constituents. Now, when you want to store all the information of your quantum state, you have to store all these amplitudes. Now, the problem is, Hilbert-space is exponential in the number of constituents, so you need exponential resources to store all these amplitudes in case you don't have an efficient compression, which we know we have for a weakly entangled state, say, in 1 dimension in terms of MPS, for instance. Now, what we are trying to do now when we want to go to 2D, 2 plus 1D, where no efficient compression is known, we are following a different approach now. So we don't aim now at storing these amplitudes, but we only want to generate them on the fly when needed. So suppose you have a machine, like with simple input and output. Input is a spin configuration, and the output of that machine is then your amplitude, or a good approximation thereof, which I denote here with psi tilde. So if you have such a machine, then you don't need to store the amplitudes, but you can generate them, and in the end, do some Monte Carlo and sample from that machine those amplitudes which you need at a given moment, but avoiding completely storing amplitudes. But of course, naturally, you might be wondering, okay, here just moving all the complexity of quantum many-body physics into the complexity of this machine, and I think, of course, like that's would also be my first impression of all that. But as I would like to show you now in the following, it is possible, at least in some cases, to construct such a machine. And the first approach I would like to show you how to construct such a machine is what we call classical networks. And in the end, what this classical network is, it's in the end some classical Hamiltonian, which I call H effective. And suppose we know such a classical Hamiltonian that taking the exponential gives us the amplitudes, then this machine is rather simple and straightforward to use. Of course, the question is how to generate such an effective classical network, such an effective Hamiltonian. The details I will show you on the next slide, but just conceptually. So what we do here is we are doing you obtain this H effective by doing some perturbatively oriented cumulant expansion, such that we expand like this effective Hamiltonian in terms of some small parameter. So overall, this is a perturbatively controlled approach, which is then further, to make it a bit better, variationally optimized.
Sorry,
yes?
a question. Is this Hamiltonian supposed to be real, or?
No, that's like a complex Hamiltonian in the end. So you can think of it, I give you an example on the next slide. You can think of it of some complicated Ising model where the couplings are complex.
Okay, very good, thanks.
Yes, exactly. So it's very similar in spirit to other kind of variational wave functions you might have heard of, like Jastrow type of wave functions or Hughes and Elsa wave functions. Now, just to flash, like in some cases, it's actually really extremely successful. So here's an example, like we have examples for quantum 1D Ising. Here for a many-body localized system, which are interacting systems of here fermions subject to strong disorder. And for instance, you can see here dynamics of the entanglement entropy as a function of time over huge scales, as you can see here. Comparing like the result we obtain using these classical networks, which are these solid lines, to the exact numerical result, which are the symbols. So in that context works really well. But also we have applied it recently to lattice gauge theories, in particular the quantum link model in 2+1D, and I will talk more about this later. So how do we obtain or construct these classical networks? So remind me again, so what we want to do, we want to determine some time-dependent quantum many-body state, which we obtain by initializing our system in some state psi naught and then doing some time evolution with a Hamiltonian H. And when we expand this in a computational basis of spin configuration, this gives us these time-dependent complex amplitudes. Now, as I said, it's a perturbatively motivated approach. So what we do is we go to some interaction picture. So we decompose our Hamiltonian H into some H naught and some V. And when we do that, like that's just standard quantum mechanics here, then you can rewrite the time evolution operator in this form in the interaction picture, where this is the free evolution, and then here the combined influence of all the perturbations that you have, and this W operator is some time ordered exponential of which involves in the end your perturbation. Exactly. So now using this expression, so up to here everything is still exact, you can express now your amplitude for a given spin configuration. So when you essentially put a bra vector S here in the above equation for the time evolved quantum state, and use the expression here on the left hand side, that's what you get for the result for the amplitude when you choose your spin configurations to be exactly the eigenstates of your H0 operator. Okay, and we assume that this H0 is always a classical Hamiltonian. Now comes the approximation. So up to here everything is exact. Now we do an approximation, and that approximation is very simple. It's doing a cumulant expansion for this object on the right-hand side, which is the complicated part, which involves the perturbation. And in first order, this gives you this rather strangely looking maybe expression, but just believe me, that's what it is. And like that's the first order contribution where V appears once, then there is a second order contribution, and so on and so forth. And depending on how much effort you want to invest, you can go in principle to higher and higher orders. Now already at this level, you can see like that you can write your amplitude in terms of some Hamiltonian which only depends on a spin configuration. So it involves, like, for instance, this classical energy that you had already and this function here. Importantly, what you get is always that this effective Hamiltonian is some local classical Hamiltonian with complex coefficients. So for instance, when you consider the 1+1D transverse field Ising chain, in first order, your classical network, this classical Hamiltonian is just of this form. So it has some constant term, which is just there for normalization. Then there is a nearest neighbor spin-spin interaction, a next nearest neighbor spin interaction. And when you go to second order, you will generate more difficult terms. And like when you go even higher orders, you will generate more and more complex terms, of course.
sorry,
Yeah.
maybe you said it, but what is H naught in, for example, like for the transverse field Ising model?
So an example given here, it's like a sigma z, nearest neighbor sigma z interaction.
Okay.
And the perturbation is a transverse field for this concrete example.
So what's the difference now between the state S and psi naught?
So psi naught. So psi naught is the initial condition, and psi naught. I was not showing that explicitly, but psi naught of S is in the end just this this overlap you can see here. So the S psi naught overlap. So the cumulative expansion is like, it's, so maybe you are it's like a bit more than conventional perturbation theory in that you're summing up subsets of diagrams here up to infinite order, and the expression in the exponent here, that's the that only has the connected contributions in the end. But it's very similar, like when you think in terms of Feynman diagrams, you're just summing up a subset of diagrams. What is now the advantage here? The advantage here is mainly that, so all of that does not depend on the complexity of your H naught. So your H naught by itself can already be a difficult classical Hamiltonian. And you can, in a controlled way, account for all these corrections. And what you get in the end is that you have to do, that you get a wave function, which you might be, like when you're familiar with variational Monte Carlo, is a simple variational wave function, which is just some kind of Ising model, where you can then do some time-dependent variation principle and just variational Monte Carlo. So just very standard things in the end.
We have online a question.
Yes,
so
please.
What will happen if S is orthogonal to psi naught?
Yes, then we have a problem. So that's a limitation of this approach. When like the smaller this overlap, or like there is one limit which we don't have under control here, let's put it that way. And that is when the initial condition is very close, or is very close to a spin configuration in that computational basis. So when many of these elements are exactly zero, or almost zero, then this cumulative expansion is not well controlled, and then it doesn't work. So in the end, it works. It always works when you're not very close, when your psi naught is not like very close to one of these spin configurations. Thanks for this clarification. That's a limitation here. Exactly. Okay. So now I would like to apply this method to a problem which is a very recent development in quantum many-body physics, and which goes under the name now of disorder-free localization. And this is a phenomenon which is unique to lattice gauge theories. And that's what I would like to discuss now in the following. And I will do this for the example of the U1 quantum link model in 2+1 dimension, like the pure gauge theory without matter. Maybe some of you are already familiar with that model. Actually, its origin is from high energy physics. And as far as I understood, like Uwe Jens Wiese was already giving a talk at the seminar, and he is the one that introduced these models. So what is this model like? The definition of the model I've been writing down here. Let me explain what it means. So within that gauge theory, we consider a square lattice as depicted here on the right-hand side. And we have spin 1/2 degrees of freedom here, living on the links of this lattice. So here, 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 and here, for instance. And we use the following convention that when we look at the columns here, that an arrow pointing upwards means spin up, and an arrow pointing downwards means spin down. That's simple. Now, on the rows, we say that a spin pointing to the right, we identify with spin up of the spin 1/2 degrees of degree of freedom, and a spin pointing to the left, we call spin down. Now, this Hamiltonian like that we were considering has two terms. Here on the left-hand side, like a kinetic term, which induces correlated 4 spin flips on a plaquette. So it flips all spins on a plaquette either when they are aligned clockwise, anti-clockwise, or clockwise in this plaquette. If the spins are not oriented, say clockwise, like here, because this last spin is pointing in the wrong direction, then this kinetic term does nothing to that plaquette. So that's one term, and the other term is a potential term, which just flips back and forth plaquettes. In the end, it measures nothing but, or counts the number of flippable plaquettes that you have in your system. Now, as I said, like, and as you might know, like this U1 quantum link model is a lattice gauge theory, and it has a local symmetry with generators, GN, which are in the end measuring just like the number of outgoing minus the number of inflowing arrows that you have here. So in that case, when you consider this vertex, say, the number of inflowing arrows is 2, and the number of outflowing arrows is also 2. But as you see here, I will also consider, for some reason, I will explain later on, also consider other cases where there are more particles, more arrows inflowing than outflowing. Say. Now, what we were now considering for this U1 quantum link model, we were interested in some non-equilibrium dynamics at high energy densities, so far beyond like a low energy manifold. And as some initial condition, we were choosing this particular one. So where, which I denote like spin pointing to the right, it means in the end that this is an eigenstate of the sigma x Pauli operator for all spins. In the sigma z basis, this is just a superposition over all spin configurations. Now, a small remark here already. That's probably not so much of a high energy physics perspective that I take here, because for the experts, I'm considering here actually a superposition over all superselection sectors. But I will come to that on the next slide in more detail. But when we were considering this initial condition for dynamics, what we were observing is the dynamics here on the right-hand side, where we monitor the spatial temporal build-up of quantum correlations as a function of like during our non-equilibrium process. And like here is time, here is the distance that appears in the definition of this correlation function. And what you can see here, these are simulations for 100 by 100 systems using these classical networks. And I claim these are essentially exact, that correlations build up here only over small distances, but not over larger distances. And that is something which you might not have expected, because the quantum link model is a genuinely interacting theory, and you might more or less expect, at least at these high energy densities, that dynamics is essentially ballistic. Maybe later on hydrodynamic regime but correlations should just spread throughout your system. There should be a light cone, but there is no light cone. Now, the question is this just slow dynamics now, or is it really non-ergodic behavior? And as I would like to show you now, this is really non-ergodic behavior, and this can be understood in terms of this concept of disorder-free localization. And that's now really remarkable because when you think about thermodynamics, in the end, thermodynamics tells you that, or like the assumption we also always take in quantum many-body physics is that if you have an interacting quantum many-body system which is homogeneous, and that's what the quantum link model is, an interacting system without like integrals of motion or whatever should always behave thermodynamically, so it should show ergodic behavior. But that's not what we find here. And what I'm claiming is this is a rather general property of lattice gauge theories. So how can this happen? So let me consider a abelian lattice gauge theory in the following. So I don't know what happens for non-abelian ones. That's something which is interesting, but I have no idea. So let's focus on the abelian ones. So what does it mean to have an abelian lattice gauge theory? It means that, okay, we have a local symmetry by definition with generators for each lattice site, which I call n here. Local symmetry means that this generator commutes with the Hamiltonian. And since we have an abelian lattice gauge theory, also these generators mutually commute with each other. Now, what does that imply? This automatically implies one very special property of gauge theories, namely that you have an extensive, like proportional to the number of lattice sites, a number of local conserved operators, namely these generators. So they commute with the Hamiltonian, so they are constant. They are described conservation laws. It's extensive, but not equal to the number of degrees of freedom, of course. But as a consequence, also that the generators commute with each other, and that's like more or less quantum mechanics 1, we know that the Hamiltonian decomposes into blocks, yes, which are characterized by the quantum numbers of the operator. So your Hamiltonian decomposes into many disconnected blocks, which we now call in the quantum many-body physics context Hilbert-space fragmentation. Like in lattice gauge theories, this is very natural, but also there are other systems which are not gauge theories and display similar fragmentation. Now, what is the consequence of this fragmentation? And this consequence of fragmentation, I'd like to explain you now in the following 2 slides. So for the quantum link model, in the end, the generators of your U1 symmetry are proportional to the number of ingoing minus outgoing arrows on a given vertex. If we would include matter, we would include in the generators also some matter degrees of freedom, so that in the end, these generators are nothing else than the Gauss law on an operator level. But in our case, we don't have matter, so like this rho is always 0. Now again, we have a local symmetry, we have an abelian lattice gauge theory, and of course, like that's related to this fragmentation of the Hilbert space. We can label all eigenvalues or the eigenstates by the eigenvalues of these generators here. That's quantum mechanics 1, and let me call the eigenvalues of these generators Q alpha. Now, what this Q alpha now define, and that's like a notion, like as far as I understand from high energy physics, that defines you a superselection sector. And a state psi of the superselection sector is always such that when you apply your generator onto that state, you these are eigenstates of these generators, and the outcome is always the corresponding eigenvalue at the respective lattice side. Now, what I would like to do is like not consider this as just a mathematical formalism, but to give these eigenvalues a meaning. So maybe actually this is all obvious for you. So like, let me apologize when I'm saying too much along these lines. But when you remind yourself that Gn is nothing else than Gauss' law on an operator level, that you can reformulate this equation down here in the following form. So by bringing the Qn to the left-hand side. So what this tells you is that you can interpret these numbers Qn, these eigenvalues, actually as some kind of charges that you have in your system. But these charges are now not dynamical, but they are static and they are in the background. So they are there, your system knows about them, but they're not dynamical objects. So if you consider a random superselection sector, so meaning a random collection of these numbers Qn, in the end, what it gives you is a system with a random background charge configuration. And now comes the catch. So, and that's probably a very quantum anybody perspective, so not high energy physics. Now, we know that like in a given superselection sector, the Hamiltonian is block diagonal by construction. So this I denote by HQA, Q alpha. And now let's consider a situation where we study some dynamics, but the initial condition is a superposition over different superselection sectors. That's denoted here. And psi Q alpha is a state in a given superselection sector, and C Q alpha is the corresponding amplitude. Then, when you do dynamics and study expectation values of operators, what you will find is because there is no coupling between superselection sectors, and in observable you have like a psi on the right-hand side and left-hand side, that in the end expectation values decompose into the following structure, into a sum over superselection sectors, with dynamics just taking place in that superselection sector. That's just because everything decouples, yeah? But now you can interpret this as some kind of an effective disorder average over superselection sectors. And this, of course, like if only superselection sectors are involved which have a strong random background charge contribution, that this can lead to localization, as you would have for Anderson localization in other quantum systems. So although your Hamiltonian and your initial condition are translationally invariant, lattice gauge theories can behave as if they were localized systems and become non-ergodic. And that's what you have seen for this quantum link model. And you can make this for the quantum link model a bit more concrete and show that for particular superpositions of superselection sectors, in the end, one can do some classical percolation theory, which shows that you're always non-ergodic. But now, in terms of progressing time.
So sorry,
yes.
I have a question. So I, as far as I understand, like this simulation that you did like with this new method, like in which like you define some sort of classical Hamiltonian.
Yes.
That defines for you. Okay. So
yes.
So in a sense, how do you know like that it's not really like the artifact of this way of approximating the problem?
Yes.
So for example, like in principle, I can imagine that you do. I'm not sure if you're able to evolve for long enough time, but in one dimension, right? You can try to do MPS studies of you know, lattice gauge theories there, and you have, I think, more control, at least like over some limited amount of time.
Yeah. So like the final statement about really that it's non-ergodic, this is not based on that method, because you're right. we don't, from that method, we never know whether this is just slow dynamics or whether this is eventually becoming really non-ergodic. But up to the time scales we study, we have some control. So like over like the accuracy. So at least we can have a good argument when we can at least trust our results. And that is that we can, for instance, increase the order of our perturbation theory and study convergence and of our result at a given time. As long as times are finite, this is fine. But of course, it will not allow us to study infinitely long times. That's not possible. So like that's one way how we study, or how can we be sure about the accuracy, is that like the order of the cumulant expansion that we do is something analogous like to increasing the bond dimension in MPS, say. When you observe convergence, you can be rather sure that things are accurate. And there's another aspect which I've not discussed here. There's a way intrinsically to measure also like to get an estimate of the error of the method itself from variational Monte Carlo. So one can estimate within variational Monte Carlo like an overall error of the quantum many-body wave function. Although that doesn't help you so much quantitatively, but it gives you an idea how accurate you are. The best thing is to study convergence as a function of the order in your cumulant expansion that you do. Concerning this non-ergodic behavior, here we have been doing something different. So because of the already advanced time, I would like to postpone it maybe to discussion at the end or afterwards. But roughly what we are doing, we are studying single typical superselection sectors. And what we find is that these typical superselection sectors fragment into different clusters of finite size, which are kinetically connected. So in the end, background charges that you have in a superselection sector, they impose such strong dynamical constraints that dynamics takes place only within small clusters. And these clusters are finite. And as long as you have a situation like this, you cannot be ergodic because you cannot communicate between different spatial regions. And that's how we show here non-ergodic behavior, but that's not based on these classical networks. Let me now go one step further. And in the end, it's a continuation of these classical networks. So we are still searching for such a machine which can generate for us these amplitudes on the fly. These classical networks are working well in some specific situations which are tailored to that approach. They are certainly not general purpose. And one thing I was mentioning also, like thanks to a question, that it depends, for instance, on some initial conditions. So some initial conditions are really bad for that approach. And also we always have to be close to some classical limit. So we would never be able to study dynamics in the vicinity of a critical point, say, because that's not what we can reach perturbatively. So of course we would like to have something which is more general purpose. And here the natural generalization nowadays is probably to use artificial neural networks. And that's in the end based on this work, which is already 3 years old now, but in the context of what I've been telling you before, it's but a straightforward extension in the sense that artificial neural network automatically realizes a machine as we would like to have it. So you can design an artificial neural network which has as some input a spin configuration. So here for 3 spins, say S1, S2, S3, then you process your spin configuration through your network with the output of the network being your desired quantum many-body amplitude. That's your output. So it naturally is such a machine to generate your quantum many-body amplitudes. But compared to these classical networks, which automatically have the limitations, this what is the key idea here is that neural networks are universal function approximators. And what that means is if you make your neural network large enough, so put enough of these hidden spins, then you can always approximate any desired function, such as our amplitude, to any desired accuracy. So what it tells you is that your desired wave function is always within your the subspace of functions, that subspace of functions you can represent with your neural networks. So as in MPS, which is where you also know that in principle, upon making the bond dimension large enough, you can represent any quantum state. You don't know whether you can do it efficiently, you just know that in principle, you can. So it means like any quantum state can be encoded in a sufficiently large neural net. And overall, which is also very appealing in that whole approach, is that the complexity of the algorithm is only polynomial in the size of the neural net, in system size, in all parameters. So supposedly, if the size of the neural net is not too large, everything is polynomial. Now, our initial belief was, okay, probably at some point, you need always such a large neural net that in the end, things explode. But it turns out not to be the problem. The problem is something else. And when you look carefully already in the initial paper, say, you observe that there are some always limitations in terms of either system size or time that you can reach with this approach. So here, that's from the initial pioneering paper, where you can see dynamics in some transverse field Ising model on rather short times here, like 1, 2, that's like almost transient. And what you can see is like already here, you can see to start some deviations from the exact result. So exact result is dashed line, and the neural net approach is the solid. And that's maybe one could wonder, okay, maybe you could improve on that situation. But there were also works which were questioning the approach as a whole. And so as I told you, these neural nets are universal function approximators. So when you make them larger, at some point, you always have to should see the convergence, because you can approximate any function. So also the quantum many-body wave function. And there was a work where they were studying, again, dynamics of transverse field Ising chains in 1+1 dimension. And what they have observed is that when the system is small, that the neural network data, these are the colored, converges to the black line, which is the exact result. All fine. But when you go to larger systems, it seems like the neural network data converges to something else consistently. It does not converge to what you like, to the exact result, which was formulating a problem saying like something is fundamentally going wrong here. And like we started 3 years ago, and it took us 3 years to understand what is the problem here. And now we think we have solved it, and to a large extent. And as an example, here's the dynamics of a 2D transverse field Ising model, where we compare like different neural networks here, but that's not super important, but also to some state-of-the-art IPEPS data for that system. And as you can see here, for instance, in the left-hand side, we get, on the one hand, like nice convergence of our neural network data for very long times. And that's what you can achieve with state-of-the-art IPEPS, up to the point where we have IPEPS data, the data collapses onto each other, agreement is perfect. But with the neural nets, we can reach now much, much larger times in some instances. Now, in other cases, we can we are more or less like reaching the same time scales like here and here, but there are other ones where we get much, much further. And let me try to explain you now in a few minutes what is the problem and how can you solve it. So in the end, like as these classical networks, these artificial neural networks, you can understand such that that you are just doing variational Monte Carlo. You have a variational wave function, and when you have a variational wave function, you solve the non-equilibrium dynamics by mapping the quantum mechanical time evolution onto a nonlinear classical differential equation for your variational parameters, which for a neural net are the so-called network weights. And this is the resulting differential equation. It is a linear, it's like the resulting equation that you have to solve. Eta dot is the change of the infinitesimal change of your network weights for one small time step. You have like some matrix S here and some forces F. Details are actually not so much important for what I would like to say. What is important to realize, however, what this time-dependent variational principle is always giving you, it's not so much machine learning as you would expect, that you have some complex manifold of network weights and you're trying to do an optimization to find like a global optimum. What the TDVP does for you, it tells you, like, suppose at some point in time you are at the global minimum of your variational manifold, how you can follow that global minimum step by step. So from one step to the next. When you solve it exactly. Now the problem is when you don't solve it exactly, what can happen at some point that you might for some while follow the correct minimum, but then there's another local minimum nearby and you're following then a different minimum. And once you follow the wrong minimum, you're lost in somewhere in your variational space and you will never come back. And that's what happened here, that you were following the correct minimum and then the wrong one, where you systematically are off from the exact solution. And the key problem here is that, so like that's again written, this equation in compact form, that you have to invert this matrix S. And the problem is S is not invertible. So what typically is used, you do a pseudo inverse where you put a threshold on singular values. But the key challenge here is that we do Monte Carlo, so noise is everywhere, and we don't know exact singular values. We don't know the exact pseudo inverse, and that's exactly what causes these problems. And what we've realized is that what you have to do in order to make these neural networks work, that you have to go into the diagonal basis of this matrix S. So you first diagonalize S. This gives you the eigenvalues sigma squared here on the left hand side and some new forces on the right hand side, which are called now rho k instead of fk. And now the key insight was from Markus Schmidt, who was the key player in all that, that when you study the signal to noise ratio of these individual quantities here, you find that on the left hand side you don't have a problem. So the you see, for instance, like singular values of this matrix as a function of time. And no matter at which scale you look at, that's a logarithmic scale here, the noise is never larger than the signal. So noise is always rather small. This is different for the right-hand side of this TDVP equation. And that is what is shown here. So these are the elements of the vector on the right-hand side. And it's showing the signal to noise ratio from Monte Carlo. And what you see is that there are many, many elements of that vector where the signal to noise ratio is really small, and only a few ones which are large. if you sample these values down here, there you just sample essentially noise. There's no information in that. And now instead of imposing a threshold on singular values, as has been done previously in these works, like putting a line here and taking only those singular values which are like above that line, what we now do is we impose a threshold on this signal to noise ratio here on the right hand side, indicated by this green line, and neglect everything which is below the signal to noise ratio threshold, and only take into account these contributions and solve the problem only for those. And that makes it stable, and this new regularization scheme in the end allows you to obtain the data that I was showing you. And allows us also to study other properties like collapse and revival oscillations of long-range order in the Ising model, and also build up of multipartite entanglement. And with this time at the end, like especially at the end, I was showing you that we have now some powerful tools that we can also start to think about doing non-equilibrium dynamics in 2 + 1D, and that these approaches are competitive or even superior to tensor networks, and have the key advantage that you can increase system size or time at moderate polynomial costs. And it's still not the network size, which is the limiting factor, but still some other remaining instabilities that we have to take into, be able to control in the future. And with this, I would like to thank you for your attention, and please go ahead if you have any questions.
Yeah, thank you very much for the nice talk. So please, one can join and just unmute, and let's clap for Markus.
Thanks a lot.
Yeah, thanks a lot. We of course have time for questions, and yeah, maybe let me directly start. Do I understand you correctly that these quenches you presented for the Ising model were for the ground state, with the initial state? Or so in particular, at least in tensor networks, it's easy to go from matrix product states, for example, to matrix operators to describe thermal states. So can you also go to finite temperature?
Yes, that's in principle also possible. There have been already studies on that. Like the simplest thing is that you can always, of course, represent your density matrix as a vector with just more elements. And like as soon as you have a vector, you can, of course, you're back to the same scheme that you're doing here. Whether there are more efficient ways of doing it, I don't know. But here it's like initial conditions were always rather simple for these dynamics, some product states which have no entanglement, no structure in it. And then we were studying the dynamics which were following out of that. So initial conditions simple, finite temperature also possible, but no one has up to now shown that you can describe or capture mixed states in a more efficient way using this approach than other ones. So in some way, like this is the first example, I would say, where although it's like the idea is old, 3 years now, this is the first example where you can see like that these neural net states can be really superior compared to other methods. Before it was only to show that they are compatible with state of the art, but here we can really go further. And I think it's not the end of the story.
So I have a question too about that, because it looks very interesting. Do you have some further, sanity checks regarding the results generated in this way? Because I understand that, like at initial times it overlaps with iPads, and later it's gonna, diverge, which is expected. But then, like the later part of this curve, like how to test
so we have in the end like a parameter where we can check convergence. So like as bond dimension in MPS. So we have the size of our network, and when we can see the convergence with the size of the network, then we are rather confident. So the point as an MPS, like it's similar as an MPS. In MPS, you also know that in principle you can encode any quantum state in an MPS formulation when the bond dimension is large enough. What you do practically is you study convergence as a function of bond dimension, and once you see convergence, you are assuming that you're in the asymptotic regime. Same here. Here, the parameter to do this is the size of the neural net. When we see that convergence as a function of the size of the neural net, then we are confident that what we get is the numerically exact result. Because again, here we know that when we go to the asymptotic regime and make the neural net artificially, like arbitrarily large, we have to we can always approximate any wave function with arbitrary accuracy.
So, sorry, another question about it. So it wasn't clear to me. So in the first approach, you started with something that was like a maximally mixed state, and I think like the system was non-critical. Like, are these 2D results at criticality or close to criticality, or?
So maybe
not really.
Yes. So like, so you can see, for instance, 3 different classes of data. Like here in the middle is the case where the transverse field is chosen such that if you were considering ground state properties, that would be the critical point, the quantum critical point of the model. So.
And is it the hardest case to solve?
Yeah,
like
absolutely.
Okay.
Absolutely. I can also show you maybe some other data that's like recent development where we study quantum Hilbert-space in 2D, 2+1D, essentially in the Ising model.
Oh, like these are some colleagues from my alma mater, basically.
Ah, I see. So you know Marek and Jacek?
Yes.
Yeah. And like there we are doing quantum Hilbert-space in 2D now, comparing also like MPS simulations and the artificial neural network simulations. And like there we are having some promising results already. But still in the vicinity of the critical point, of course, things are most difficult. But we don't, the point is a bit still, we don't, so although we have it under control now, like that we get results consistent or a bit better than with tensor networks, there are still some remaining instabilities which we don't understand. So why we cut off here at this time and don't let it go longer is that something is happening here, like some instability, and it's not the network size, or that it would require too long simulation time, or like a compute time. That's not the point still. So we are still trying to solve like other problems of the algorithm itself.
Hi, Adrian Fagan here. Quick question. So can this issue be related to the entanglement growth? Can the network actually represent highly entangled states with long-range entanglement?
Yes. So although that is not like understood in general, like a disclaimer in the beginning, but what has been shown rather in the early days, like already 2-3 years ago, that there are some volume law entangled states which are trivially encoded in artificial neural networks. So with almost no complexity, like in terms of artificial neural network states. But this does not mean that all volume law entangled states can be represented by this neural net. And I actually don't believe so. So I don't think that we will be able to solve all problems using these neural nets. But at least up to what we have seen, neither entanglement nor the complexity of the wave function itself is the issue. It's an issue of encoding the quantum state into the neural net. it's a measure of training. It's not a measure of complexity or size of the net.
So with this, you mean that by increasing the number of hidden variables, you don't get an improvement?
No, that exactly. So that, like here you can see like various different curves with different color. These are all different neural nets with increasing complexity. And only on the left-hand side, you see like that this one is a bit different behaving than the others. But like with the size of the neural net is not at all a problem. Everything converges as a function of that. It's the problem that like at the point where we stop showing the data, something is happening. Yeah, something is exploding numerically. You get nuns, you get things like that.
I see.
So really numerical instability.
Mm-hmm.
And it's not the like, we don't get, like, it's very hard to get the information into the neural net. The neural net would be able to host the information. It's like complex enough to hold all that information, but you don't get this information in. That's the problem at the moment.
All right, thank you.
I hope at some point the problem will be not the training, but really the size of the net. So I think at some point this problem has to come in. But currently that's not the issue. We are like one step before.
So you mean this could be an issue with the natural gradient descent or whatever algorithm you're using?
The point is a bit like that we are doing less machine learning that I would like to have here. So we are, I was mentioning this briefly before, that how you solve this is using this time-dependent variational principle. And this time-dependent variation principle assumes that you, at a given point in time, you are in the global optimum of your variational manifold or of your neural network weights and the optimal point. And for an infinitesimal, when you do an infinitesimal time step, you assume that like your variational manifold does not change so much. And the TDVB tells you how from one time to the next, you just have to follow the maximum. So you can think of it as some local optimization, but never global. And that's the problem. Once you are not following the global minimum anymore, you will never come back because you're only doing local optimizations.
I see.
And what we would like to do is global optimizations, of course. And we had some attempts, but this turns out to be extremely tricky.
So related to that, there is a question online from Ising. So is it possible to increase the variational manifold to avoid the wrong minimum?
Yes, that's something which points like in an interesting direction. I would say that there are some networks which have strong instabilities than others. And some of, like, we don't understand this completely, but only some aspects. So what we, for instance, find is that, and somewhat natural in retrospect, that there's some neural networks which have built-in notion of locality. So there are, for instance, some neural nets which are always have very long-range couplings where you don't have any notion of locality, but there are others which are in particular called convolutional neural networks. They have a built-in notion of locality. And of course, we know that Hamiltonians are local. And that, for instance, has also helped significantly in this context. So use these convolutional neural nets, because as we understand, they provide you with a much more suitable variational manifold for your optimization problem, because they naturally realize one of key property that you have in for local quantum many-body systems, and that is causality and locality.
And does the network size in your results actually refer to the number of hidden layers or total number of nodes distributed over all the layers?
So you can see various strange numbers. So like that's like a way to some convention how to describe the structure of convolutional neural networks. But in the end, honestly, as long as you use convolutional neural networks, details only hardly play a role. You can play around and just choose one, but this typically works out. The problem is more on a different side. So like maybe just one thing to say here is that the number of variation parameters we have here, or the size of the neural network, is much, much smaller than the Hilbert-space size for these problems. So the system size here was like 10 by 10 in Rydberg-space. So these are 100 spins. Hilbert-space is something like 2 to the 100, but we were using only, I think, about a few hundreds to 1,000 variational parameters. So much, much less than Hilbert-space size.
Right. If no one is asking questions, may I ask another one?
Please.
So in the time-dependent variational principle, when you apply to neural networks,
yeah.
Does the principle tell you basically how to change the weights as you evolve in time?
Yes.
Or you'd have to carry out also a projection or minimization like you do when you look for the ground state?
Somewhat what it does is like the following. So given you have at one point in time, like your wave function is given by your variation wave function, then you do a time step, like with an exact time step, and project back onto your variation manifold. And you can when this time step is infinitesimally small, then you can formulate this in terms of a ordinary differential equation, which is nonlinear for your variational parameters. So all these functions f and s here, they are all functions of the network weights themselves. So it's a highly nonlinear equation, and so it maps quantum dynamics onto like a nonlinear classical ODE for these variation parameters, and corresponds like to an attempt to always find like optimize locally, search locally for the optimal optima.
I see how it works. So basically you do sampling to get this matrix S, and then
yes.
you solve the differential equation, you get the new coefficients, and then you do sampling
exactly.
to measure basically.
Exactly. But the problem is that in order to solve for the couplings, you have to invert this matrix.
I see.
And the problem is that this matrix is not invertible. Like this I can guarantee. It's never invertible. And when it's not invertible, you have to think about some regularization that you have to do. And what I am wanted to say is like it depends crucially on the regularization. And the standard regularizations that you do, like taking pseudo inverse, they don't work. Don't try to do it. What you have to do is should use a regularization which takes into account for the signal to noise ratio of the quantities that you sample, because there are some matrix elements which have large signal to noise ratio, some which have small, and you should only take into account those contributions which have a large signal to noise ratio.
Thank you.
Are there further questions? If not, then yeah, let's thank Markus again.
Thank you very much.